now let's consider what happens in the case where we have a stationary observer and a source moves past the observer. Joe Wolfe explains this very well again, so let's cut back to the phys clips and look at how Joe explains this.
Now let's have a moving source with speed v sub s. The source, s, is in a different position when it emits each wave peak, so the circles are no longer concentric. The wavelength is decreased ahead of the source and increased behind it. In time t, the wave spreads vt, while the source travels vst. The wavelength is therefore decreased ahead of the source by a fraction, vs on v. Behind the source, the wavelength is increased by the same fraction. Now the wave still travels at speed v, so a stationary observer hears f dashed equals v over lambda dashed, and substitution gives this expression for the new frequency. Here we take vs as positive if the source approaches and negative if it goes away.
So Joe's just derived for you f dash is equal to f over 1 minus vs on v. Now let's just rearrange this a bit. If we times both the top and the bottom by v, so we're multiplying by 1, so that's allowed, then we end up with f. We'll pull this f out the front, and we've got v over v minus vs. So this is the equation that describes what happens to the observed frequency as a source approaches the observer.
So we've seen that when an observer is stationary and the source is moving, we can write the equation as f dash, the frequency observed by the observer, is equal to f, the frequency produced by the source, times the velocity of waves in the medium divided by the velocity of waves in the medium minus the velocity of the source, which is written as v subscript s. Now that's what happens as the source approaches the observer. If the source is moving away from the observer, then we need to change the sign in front of the vs term, the velocity of the source. So in the case that the source is receding from the observer, we have the equation f dash is equal to f times v over v plus vs. So let's look at a problem now where we can use these equations to solve it.
So the question is, your clock radio awakens you with a steady, irritating frequency of 600 Hz. One morning it malfunctions and cannot be turned off. In frustration, you drop the clock radio out of your 4th-story dorm window 15 meters from the ground. Assume the speed of sound in air is 343 meters per second. As you listen to the falling clock radio, what frequency do you hear just before it strikes the ground? So let's start by drawing a diagram. Here's you dropping a clock radio out the window. You're 15 meters above the ground and the clock radio is going to move away from you. Now you're the observer and the clock radio is the source in this case. So it's a moving source. So we've got that f dash is equal to f, and then we'll have v, and in this case the source is moving away from you. So if it's moving away from you, we have v plus vs. We know v, that's 343. We know the frequency that the source produces, it's 600 Hz. We've been asked to calculate f dash, the frequency just before it hits the ground, but in order to do that we're going to need to work out the velocity just before it hits the ground. So to do that we're going to need to go back to those kinematic equations. So we're going to need to use the formula v squared equals v naught squared, so the final velocity squared equals the initial velocity squared, plus 2a times the distance. Okay, so v squared, that's the velocity of the source squared just before it hits the ground. You're dropping it from rest, so this is 0. Now, it's accelerating downwards at 9.8 meters per second, and it's falling downwards, so its displacement is minus 15 meters. So both these are downwards, so they have negatives. And so we've got 2 times 9.8 times 15, so that's 294. And so Vs is equal to the square root of 294, which is equal to 17.1 meters per second. So now we've got everything and we can substitute into this formula. So F dash is equal to 600 times 343 over 343 plus 17.1. So solving this on the calculator, we get 571 hertz. So that's the solution to that problem.